In this video, I will explain you concept electric flux. Now let's see the definition first. Electric flux is quantity of electric field linked to an area in that point. So simply I can say that when in an electric field, when we are taking an area, total number of field lines passing through that area. Say for example, let's say we have electric field lines projected in this way. So in a space, this is the electric field lines projected. So field lines are going in this direction. Okay. Now I'm going to consider an area. This is my area element. Now when I'm keeping the area in the electric field line, the total number of field lines passing through the area is nothing but electric flux, or it is defined in this way. So here number, instead of mentioning number, you can say total quantity. That will be a better definition. Electric flux is quantity of electric field. See, out of this electric field, the quantity that is linked to an area in that point. So when I'm keeping my area in this way, I know that all the field lines are linked with the area. Now at the same time, the area, if I'm keeping in this way, what will happen? Is the electric field lines is linked with this area? No. See, this is the electric field line. None of the electric field lines will pass through that area. See, I can keep my area in this way and also in this way. But when I am keeping in this way, see, field lines will go in this way without linking with that area. But I am keeping in this way, it will pass through that area. Okay. So we know that this quantity is dependent on electric field and also area. Not only area and electric field, and also the orientation of area. Now always area is a vector quantity and its direction is taken perpendicular to both length and breadth, because area is L cross B, length into breadth. This is a vector. Sorry, this is a vector multiplication. Yes, cross product it is. So this is the direction of area. So direction of area will be in this way. Now I know if this one is my direction of electric field and if this is direction of area, we know that flux is maximum when both of them are in the same direction. I'll repeat it. See, the green color is the direction of area. Now field line is also in the same direction. So what is the angle in between area and field line? It is 0. Okay, so when the angle is 0 in between electric field line and area, we are getting the maximum value. And at the same time, see, when I am rotating area in this way, this is the direction of area, perpendicular to the surface, and this is direction of my electric field line. When they are perpendicular, these electric field lines are not getting linked with this area. Okay, that is not passing through the area. So when theta is equal to 90, the flux have to be 0. When theta is equal to 0, the flux have to be maximum. And what is that function? This is cos theta. So cos 0 is equal to 1 and cos 90 is equal to 0. So we know that flux is nothing but is directly proportional to area, and flux is directly proportional to electric field, and flux is directly proportional to cos theta, angle in between E and A. So we will bring everything into one equation. This will be equal to flux is equal to a constant into EA cos theta. So the constant is 1 here because it has defined in that way. So EA cos theta. So EA cos theta can be written as E dot A. So E dot A, dot product of two vector, A dot B is AB cos theta. So flux is equal to EA cos theta or E dot A. Okay, now, so here in this case it will be as A is in this way and the direction of A is in this way. Both of them are parallel, angle is 0, so that will be EA cos 0 EA, simply here. Now I am going to consider a surface in this way and electric field. This is from a source charge. Now we know that these distances are completely different. So electric field at this point will be different as compared to this, and here at every point electric field is different. Now how to get the total flux linked with this area? What we will do, we will split all these parts into number of areas. So this is one area, another area, another area. So similarly we will split the whole area into number of small area element. Now this is at this point, what is the direction of area? Perpendicular. Now we have an angle here. We can easily find flux here. What is that? E1 cos theta, theta 1. I got flux here, that is phi 1. Now I will go to next area. So let's say my next area is here. Now this is perpendicular and that is the direction of area, and the angle is theta 2, for example. So here the flux is equal to E2 into, sorry, this is E1 A1 cos theta 1. Here it is E2 A2 cos theta 2. That is the flux. At E3 the normal is in this direction and this is A3, angle is theta 3. So flux is equal to E3 A3 cos theta 3. Similarly, E4 A4 cos theta 4, E5 A5 cos theta 5. Similarly, you find flux with all the area you have considered. Then add all the values. We will get the total flux linked with this area. So this can be done with the help of integration. How? We will integrate from here till here all dA elements. How? By doing a operation in this way, E dA cos theta. What is E dA cos theta? So if you are considering a small area, then this area will have a total linkage of d phi flux. Okay, so this one is d phi 1, d phi 2, d phi 3. So we are integrating all d phi. So d phi is nothing but E dA cos theta, and dA is the small area we are considering. So anyway, application is very less. I have just told you the concept. Now this one is very important. When we have a closed surface like this, let's say the area electric field is passing through the closed surface. Very important this one. Okay. Now we know that electric field is linked with this surface 1, and also will be linked with 2 and 3, and also will be linked with this surface 4, and this face, your facing surface 5, and the other facing surface 6. There are 6 surfaces. Now electric field is getting linked with all the surface, but here there is a problem. What will be the direction of area? See, for this plane, for this side, I have 2 perpendicular possible for the surface. One is in this way, so this is a surface. For example, this one is a surface. Now this is a perpendicular and this one is also a perpendicular. So which perpendicular we do consider? See, if we are considering this as the perpendicular, then we know that this, our area and electric field is parallel here. The angle is cos 0, angle is 0, so that will be EA cos 0, that will be EA. But if someone is taking our area direction as this one, then this and this is making an angle of 180, so that will be EA cos 180. Cos 180 is minus 1, that will be minus EA. So with some students they will get plus EA, with some other student they will get minus EA. This is not fine, right? That creates an ambiguity. So always with a closed surface we will take area as the perpendicular which is outward. So this is inside the closed surface. Now the perpendicular which is directed outward. So from inside surface directed outward. This is an area. Okay, now with this surface, this is the area vector. Now with the bottom surface, this is the area vector. Now with the top surface, outward, that is the area vector. Now with this surface, this one, so coming on. Now with that surface, onto, into. So in this way you have to consider area. Always it have to be directed outward, not inward to the closed surface. Now how to get the total flux linked with the closed surface? We have how many surface? 6 surface. So total flux linked with the closed surface, so this is closed, is equal to how many surface we have? We have phi 1, we have phi 2, we have 5, 3, 6 surface we have, right? 5, 3, 5, 4 plus 5, 5 plus 5, 6. We'll try, in this example, let's consider E is a uniform electric field and all areas are the same. So with this side, we know that this is area and this one is electric field. So that will be E into A into, what is the angle? This and this, cos 180. Cos 180 is minus 1. Now phi 2. 2 is the top surface. See, area is in this way and E is in this way. So cos 90 it is. See, EA cos theta. So here area is in this way, electric field is in this way. Angle is 90, cos 90 is 0. So phi 2 will be 0. Now what will be phi 3? 3 is bottom, right? Here area is in this way, field is in this way, angle is 90. EA cos 90. Cos 90 is 0. So this will also be 0. So I will make the point here. So E2 A2 cos 90, E3 A3 cos 90. So that is the reason this has become 0 here. 0. Now 4 is this surface and area is in this way. Electric field is also in this way. So EA, angle is 0 here. So EA cos 0, 1. Now fifth surface, this one. See, area is in this way. Electric field is in this way. 90. Cos 90 is 0. So EA into 0 will be 0. That will be the same case for 6 into. So this is area and this is electric field. The angle is 90. See, this is the angle. 90. So cos 90 is again 0. So this will also be 0. So 4 zeros and other values are minus EA plus EA. What is the net flux? 0. See, though there are electric field and linkage with area, the net flux of a closed surface here in this example has become 0. So this is a very, very important area and this gives the foundation for your upcoming topic, which is Gauss's theorem. Okay, so be very clear with this and thank you.